All right, Mr. Fish, I think we need to get going.
Last standby. Attention on deck. All present.
All right, take your seats. All right, the quiz went much better this time. 85% average, so that's a win for me. I did want to mention something about question number 4. I did not grade the first part. This was a question that was asked of me to put on my quiz by somebody who's doing a study of what some people did last semester. Were in Adam's first group and the rest of the SC 111, and trying to analyze whether people in one group did better than the other. So I thought this was kind of a poorly worded question, and so I didn't grade this, other than just that's part of the study that's being done. But what I was looking for, if I were to grade this, is that you've got sodium sulfate in water, and so you would expect that to have sodium ions, sulfate ions, and water, right? So there would be 3 answers. One would be sodium ions, one would be sulfate ions, and one would be water. The water, I wouldn't expect you to put anything for the concentration, but for the sodium ions, right, some people, what would be the concentration of sodium ions in that solution? 0.2 mole out, right? And the sulfate would be 0.1 mole out, right? So that was the correct answer for that, but I didn't take off any points if you missed anything there. All right, anybody have any issues before we get started today? All right, everybody realize that the lab, I sent out an email, a reminder this morning, the lab is solely going to be based on what you do on the computer. Right? You're going to input your data and analyze your data with the computer. Right? So other than the pre-lab. Right? So the pre-lab that you did plus that computer assignment. Tomorrow's lab, I'm not going to have you turn in the lab. I'm going to try something where you will turn in the spreadsheet that's required for it. In other words, you're going to make a plot. I forget. It's I think the mass of the solute versus the moles of the solute, and from the slope you get the molar mass, right, of the compound, right? So you'll turn in that spreadsheet. You'll do the pre-lab, and then I'm going to give you a quiz next week on Tuesday, right? So the spreadsheet will be worth 10 points. The pre-lab will be worth 5 points, and then the quiz will be worth 35 points. And on that, when you take the quiz, you'll be able to bring your lab report with you, and if you've done all the problems, then it should make the quiz pretty easy, because the questions are going to be exactly like the questions on the lab, right? So it's up to you how much you want to prepare for the quiz. Yes.
You still want the lab printed out?
Yes, I do expect you to still come to lab with the lab printed out, because you have to follow the instructions of the lab. So, yeah. All right, so we did this problem using the method of initial rates, right? We were talking about rate laws, and we came up with a final rate law with a rate constant, but we never did answer the last question. So hopefully you'll get your mind back into what we were talking about last week. We were talking about rates of chemical reactions, which can be described by something called a rate law. All right, so in this is the worksheet for this chapter. So this chemical reaction is 1/2 order in A, first order in B, and second order in C. And so if for part B says what will be the rate of the reaction under these conditions, all right? We've got different rates under different conditions, but these conditions are different than the ones up there. So we've got 4 rates, but we want to find out what the rate would be for this 5th condition. So how would I calculate the rate of that reaction if I'm given the rate law and the rate constant? Anybody?
Plug in the concentration.
Plug in the concentrations and put in the rate constant. Right? The rate constant is equal to 79.1 molar to the minus 5/2, seconds to the minus 1. Then we would put in the concentration for A that's given, which is 0.5. Concentration of B is 1. Okay, now that's the 1/2 power. That's the first power. And then C, I put in 0.01. And then I have to square that. And under these concentration conditions, that rate law will allow me to calculate what the rate is. Right? That's what this chapter 14, is all about, being able to determine rates of chemical reactions. 9.1 times 0.5 to the 1/2 times 1 and times 0.01 squared, which I get to 55.9 times 10 to the minus 3. So this would be 55.59 times 10 to the minus 3. And what would the units on that be?
I think it's just 55.
Oh, is it? What did I...
I got 5.5.
You got...
Oh, yeah. Never mind.
Wait, 79.1 times 0.5, square root of 0.5 times 0.01 squared. So is that... Do I have that right? Okay. If you don't have, if you didn't do 0.01 squared, it sounds like you get that number. Right. And what would the units on that be? Molarity per second. Right, that's always the units on rates of chemical reactions. The rate constant is such that when you determine the rate, it will be molarity per second. All right, so that is very important. I can guarantee you that on Thursday, when we take the quiz for this chapter, there will be some kind of method of initial rates problem. Look at the old quiz questions, old quizzes that I've given, and you'll find that they all have one of those type of problems on it.
Wait, Professor,
Yeah.
can you put that back up real quick? Why did you, when you were finding out your K, why did you divide 0.05 divided by 2?
Because this is given as the d dt, and there's a 2 in front of the d.
Oh,
Okay, good question. All right, now we're going to do something called integrated rate laws, which are very useful. Integrated rate laws. We just did differential rate laws, which are just called rate laws. All right, so integrated rate laws allow us to predict into the future what the concentration of something will be. Right? And what that depends upon is the type of order of the chemical reaction. So we'll start by looking at A goes to form B for a first order process. All right, so we're told it's first order in the reactant A. Okay, so what does that mean the rate law is equal to? If it's first order in A, it's going to be K, rate constant K, times the reactants raised to some power. And what power is it if it's a first order process? 1, right? So there's our rate law for a first order process. What is the definition of the rate of this chemical reaction in terms of A? Looking at the reactant, how do we define what the rate is? Very first thing we talked about in defining a chemical reaction. All right, so since it's a reactant, we would start with a negative. And then there's a 1 there, so we don't have to divide through by anything. And then what is the rest of that? It would be D, A, dt. All right, that's the way we define. I don't know if I still have my notes. Yes, I do. Remember? We did this stuff right there, and we came up with the definition of a rate. Minus 1 over A dA dt. All right. So that's how we define that rate. All right, so first order, and that's the rate. Rate equals rate. Rate equals that, K times A. All right. So this stuff right there is a certain kind of equation. Anybody know what we call that kind of equation? We have a whole course that most of you will be taking. Yes, that is a differential equation, right? It's a differential equation which you will take a course on how to solve differential equations. This happens to be one of the simplest differential equations, right? So the way to solve this type of differential equation is to separate the variables and integrate, right? So we want to get two variables here. We've got a t and an a. All right, so we want to separate and put the t's on one side and a's on the other side. So I will take this dt and multiply it through by both sides by dt and then divide through by a. So that will give me, and I want actually the negative sign to be with the kt. So this becomes dA over a equals minus k dt. Right? That's just some algebra steps. Take minus dt and multiply that by the k, divide through by the a. All right, so that's algebra. All right, so differential equation, which, Mr. Fish, put that computer down, and Mr. Franshaw, you do it too. Anybody who's got a computer. Cox and Fox, please put your computers down. I want you to be paying attention to me.
Is the negative always on the opposite side of the
I could have left it on the other side, just because I know what I want to have. I put it over there. You could have it on either side and solve that differential equation. It'll still work. Okay, so when you have these separated, you got the a's on one side and the t on the other, you integrate. Major splash, spill, or what's that? All right. So on t, we normally start at time 0 and go up to time t, something time later t. And we've got A0, which represents what the concentration is at the start, up to A that's at time t. At time t. All right. That's what the concentration will be later on. All right, which we might be interested in. In fact, many times we are interested in that. All right. So, for those who are good at integrals, what is the integral of the a over a? ln of a. So that's ln of a, which we will go from a0 up to a at time t. And then another difficult one, minus k dt. What is the integral of a constant times dt, integrated over dt?
t.
Yeah, so it's minus kt going from 0 to t. All right, so this becomes log of a at time t divided by a naught equals minus kt. All right. That is the integrated rate law for a first order process. If you take e to both sides and then multiply through by a naught, you get this relationship. A at time t is equal to a naught e to the minus kt. All right. Which means if we plot the concentration of A versus time, and this is the equation that is represented by that chemical reaction, what will that plot look like? Start here at A naught, and will be a exponential decay. Right, first order exponential decay.
Professor,
Yes.
this equation is given on the equation sheet, correct?
Yes,
Okay.
that's correct.
So you're just showing
How it came about.
Okay.
I mean, I guess I could start this and say, here it is,
Yeah.
believe it.
Okay, I was
But
just a little confused.
hopefully you understand where it came from. All right, so comes from first principles of chemical kinetics. Okay, if instead I plot log of A versus time, then what's that going to be? Well, this, I could rearrange this to be log of A time t is equal to minus kt plus the log of A naught. All right. So all I've done is I've split this up into two, which log of A minus the log of A naught. Everybody buy that? And then just brought the log of A naught to the other side. Okay, so that represents the equation for the log of A as a function of time. So what is this going to look like? This has an equation of y equals
It's going to be a
mx plus b. It's going to be a nice straight line. And what does that slope equal to? Actually, minus k. The slope m, see t is the variable, so m is equal to minus k. Right? It certainly is a negative number, right? It's going down. Negative slope. Okay? So that will be useful to us when we want to determine the order of a reaction differently than what we talked about before. And you'll see that after we do it a little bit more. Something called the half-life, with the symbol T1/2. Anybody know what the half-life is? Yes?
That's the time taken for a radioactive material to decrease in mass by like a half.
Well, it doesn't just have to be radioactive, right? But it does. It's the time required in the chemical reactions. It's time required for the concentration to be cut in half. Time required for the concentration to be decreased to 1/2 the original value. Okay? So, if you start with 1 mole per liter, it will take a certain amount of time to cut in half to 1/2 mole per liter. Right? That amount of time represents the half-life. So, if this is 1 molar, and right here is 1.5 molar, and come over here, come down there, that is T1/2. Okay? So, at T equal to T1/2, what does A of T equal to in terms of the initial concentration? After 1 half-life, what is the value of A of T?
1/2.
It's A naught divided by 2. All right, so we go back to our original equation for first order process. So I replace A of T with A naught over 2 divided by A naught is equal to minus K T1/2. So when T equals T1/2, then that's going to be true. All right. So this simply becomes log of 1/2. Anybody know how log of 1/2 is related to the log of 2? Any relationship between the log of 1/2 and the log of 2? It's almost the same.
Wouldn't it be the reciprocal?
It's not the reciprocal.
Negative.
It's the negative. Right? That becomes minus the log of 2. Log of 1/2 is minus the log of 2. You can check it on your calculator, which is equal to minus K T1/2, which we can solve for. T1/2 is equal to log of 2 divided by K, or K is equal to log of 2 divided by the T1/2. Both are useful equations. This is for a first order process. Okay? So, if I have a chemical reaction that I know to be a first order reaction, which I have one right here. Okay, this is a first order reaction, it's plot. What is the half-life for that chemical reaction right there? 100 seconds. Starting at 1, go down to 0.5, 100 seconds. What is the rate constant K for this?
2 over 100.
That is correct, or 0.693 divided by, so 6.93 times 10 to the minus, what, 3? Yes?
What does it mean to be a first order reaction?
It means that that has an exponent of 1. Okay. So if you have a rate that looks like that, then it will have a concentration profile that looks like that, an exponential. And you can tell what the half-life is right away, and you can determine what the rate constant for the reaction is, if you know it's first order. Okay?
Notes up first.
Pardon me?
Can you put the last page of notes up for us?
That one?
Yes. Thank you.
All right, so let's try this for a second order process. All right, if it's a second order process, then what does that mean the rate law is? Crenshaw, what do you think? Second order process. What would the rate law be?
Would it be the next derivative?
Which next derivative?
Because you took the...
Well, I'll give you a hint. It's K times something. Okay, it would be the concentration of A squared. Okay? Now, what would we define the rate for this reaction A goes to form B? What would be the definition of the rate for that reaction? Starts with a minus.
Minus dA, or minus d concentration of A over dt squared.
No, not squared, right? It's just, that's the definition of the rate. If this had been a 2, we'd have a minus 1/2, right? That's the way we define the rate of any chemical reaction, no matter what the order is. Right? We could have done it in terms of B, but then we'd have 3 variables, and we don't want that, right? So we're going to do it in terms of A. All right, so now, this is again one of the simplest type of differential equations. All right, how do you think we're going to solve this? Separate and integrate. All right, so this is going to, now here I'll leave the negative sign over here. dA over A squared is equal to K dt. Okay, so I'm going to integrate. Again, going from 0 times 0, the initial time we're going to call 0, and go to some time t later. And we'll start with a naught and go to the A at time t. All right, anybody know what the differential equation of the integral of dA over A squared is?
Negative 1 over
Negative 1 over A. That's correct. But since we have a negative sign there, what does that become?
1 over A.
Just 1 over A, which we go from A naught to A at time t. And the integral here is just kt going from 0 to t. So we will get 1 over A at time t minus 1 over A naught is equal to kt.
Can you move that up?
And then we will bring the A naught over there, so you get that 1 over A at time t is equal to kt plus 1 over A naught. All right, so there is the integrated rate law for second order reaction. And what is the usefulness of this equation? Well, it's linear if you pick the right variables. All right, so if we make a plot of this, right, of A versus time, then you'll get something that looks like that. If I make a plot of log of A versus time, do I get a nice straight line? Nope. I get something that's still curved. But if I make a plot of 1 over A versus time, what do I get? And which way does it go? Up or down? It will go up, like that. Because the slope of that is equal to
Okay.
K. Now, what is the usefulness of these integrated rate laws? What do they allow you to do?
Figure out the future.
Yeah, determine at any time in the future what the concentration will be. For chemistry, that allows you to calculate a concentration. But these integrated rate laws don't just apply to things in chemistry. If we, for some reason, had some kind of poisonous, noxious chemical that was released out of a lab in this building, all right? And so that we had chemicals in the air. The ventilation system for this, for the building, is a first order process, right? It depends on what the volume of the building is and the flow rate through the filtering system. So if we know what the concentration is when the accident occurs, we can calculate when it will be safe again to go back into the building, right? So you have, for first order process, right? You just figure out, you solve for the time that's required, in this equation right here. Find out what the safe level is, what the initial concentration is. The K will depend upon what the volume is and the flow rate through the system, and so you can solve for the time to when it will be safe to go back into the building. Right. In electrical engineering, many of you will take electrical engineering courses. RC circuits, resistance capacitor circuits, decay by a first order process, right, which depends on the capacitance and the resistance used in that. LC circuits are first order decays, right? So there are also, and radioactivity, which was mentioned before, is a first order decay process, right? So if you have a reactor compartment where you've got fluorine-18 present in there, has a decay, a half-life of 2.8 hours, right? And you know what the safe level is. You can calculate how many hours you're going to have to wait until it's safe to go into the reactor compartment, right? So that's the usefulness of these type of processes, right? And so we look at our learning objectives. Oh, I still need to do the half-life for the second order process. All right, so here's our second order process. Again, half-life has the same definition for a second order process. At T1/2 equal to, at T equal to T1/2. At T equal to T1/2, what is A at time T equal to? For a second order process now. At T equal to T1/2, what is A at time T equal to? At that value of T. By definition of the half-life. Nobody?
I want to make 2 over K.
Nope. Yes?
A0 divided by 2.
That is correct. A0 divided by 2. That is the definition of what occurs at the half-life. Half of what it was that you started with. Okay, so now we put that back in over here. So what is this value at the at T equals T1/2? That would be 2 over A naught equals K times T1/2 plus 1 over A naught. Okay, and now we want to solve for T1/2. Okay, so that, if I subtract that off, that gives me 1 over A naught, and that will be 1 over K times A naught is what the half-life is for a second order process. Or if you want the other one, K is equal to 1 over T1/2 times A naught. All right, so we have two equations for half-lives. One much more useful than the other one. All right, anybody know what's wrong with a second order process and the fact that that equation for the half-life? What compare that to the half-life of the what did I do? Okay, so here's the equation for the half-life of a first order process. Here's for a second order process. All right. Why is this one much more useful than this one? Yes?
Only 2 variables.
You mean here you've got T1/2 and K, here you've got T1/2 K and A naught, right? That is correct. The half-life in a second order process depends upon what the initial concentration is. So what does that mean is happening to the half-life as a reaction proceeds?
Changes.
It changes, right? It gets bigger and bigger, right? Whereas, as for a first order process, the half-life stays the same, right? So if we look at the first order reaction here, we go from 1 to 0.5, it's 100. Okay, so where would I go from 0.5 to get the next half-life? 0.25. So I come across to 0.25, it's at 200. Does that mean now that half-life is 200? No, because you went from 100 to 200, and so that means that next half-life is 100, right? And then going from 200 to 300 is what the 0.25 down to 0.125 would be, right? So the half-life is staying the same for a first-order process, okay? This is what a second-order process looks like. What's the half-life for this reaction right here? To start with, it would be 100, right? Okay, but let's say now it's at 0.5. What's the half-life in going from 0.5 to 0.25? It would go all the way out to 300. So it's from 100 to 300. So now the half-life is 200 seconds. Right? So it doubled. By cutting the concentration in half, then that will then double what its half-life is. So that's the problem with half-life. It's not nearly as useful because it depends upon what the initial concentration is. Could you determine what the rate constant is by that plot right there? Right, we could determine the rate constant here. Remember, we could actually look at this and see what K is. Can we do that for this one? Yeah, just again, we can start with 1 molar and go over it, get the half-life is 100 seconds, and then plug that into our equation for the half-life of the second order process. Right? We can still determine what K is by putting in the half-life and what A naught is for that the A naught that results in that half-life, and still get the value of K. Right? And that will work even if you do the next one. If you go from 0.5 over to 300, right now the concentration has been cut in half, but the half-life is doubled, right? So it still gives you the same value of K. All right, now, see what we've learned so far, or at least what I've tried to teach you. Recognize integrated rate laws. Be able to use integrated first order and second order rate laws to find the value of one variable given the values of the other. Right. So we have those two equations. Explain the concept of reaction half-life. Describe the relationship between half-life and rate constants, first and second order reactions. Okay. Determine the order of the reaction from plots of concentration versus time, log concentration versus time, and 1 over concentration versus time. All right, so I think in your worksheet, I think there's a problem like that to illustrate that. So the point here for this is, if you make 3 plots like that, and 1 over A versus time is the one that's linear, what does that tell you about the order of the reaction? It's second order reaction. If instead you make those 3 plots, and it turns out the log versus time is a straight line, what does that mean?
First order.
It's a first order. Now, if you make those 3 plots and A versus time is a straight line, you know what that means? It's 0th order. All right, so that's what you're going to do, not for tomorrow's lab, but next week's lab. You're going to look at the reaction of dye plus hypochlorite. And for the dye, you're going to measure what the concentration of dye does over time and make 3 plots. You're going to make one that has concentration versus time, one that's log concentration versus time, and the other is 1 over dye concentration versus time, to determine what will that help you determine. Mr. Franshaw, you're a section leader. What will that help you determine?
Not sure, sir.
All right, I really encourage you to pay attention in class. Right, it's much easier to learn as I'm talking about this than to try and do it on your own. Right, so I really do encourage you to do that. I want everybody to do well in my class. I think you'll do better if you pay attention. All right, so if you make those 3 plots for dye, dye versus time, log of dye versus time, 1 over A versus time, what will that allow you to do to determine for the dye? Yes?
Figure out what order.
Figure out what order of the reaction is for dye. Right? If it turns out 1 over dye versus time is a nice straight line, then you know it's second order in dye. All right, so that's next week's lab. Tomorrow you're going to determine some freezing points. So we're kind of a little behind in our labs. All right, so pull out your worksheet if you haven't already. I did talk about the worksheet problem number 4 to start with. All right, so question number 5. The decomposition of N2O5 is first order. At 64 degrees, the rate constant is 4.82 times 10 to the minus 3 per second. What's the rate when the N2O5 is equal to 0.0240 molar? All right? So somebody's interested in this chemical reaction, and we're interested in knowing what the rate is when the concentration is 0.0240 moles per liter. Anybody have any idea how we would calculate the rate given that information right there? Yes?
Well, the rate is equal to K times the concentration of N2O5 squared.
Why did you square it?
I was first order. Never mind.
Okay, yeah, it's first order, so it would be K times N2O5 to the first power, right? Like that. Okay? And so then what do I do with that?
You have both.
I have K and I've got the concentration, right? So that'd be 4.82 times 10 to the minus third inverse seconds times 0.0240 molar. Right, and that will give me what the rate is under those conditions. Uh, 1.16, that's good to 3 significant digits, times 10 to the minus 4 moles per liter per second. All right, so now we want to know what the concentration will be 431 seconds later. We know we're starting with 0.0240 molar, but we want to know what it is into the future, 481 seconds later. How do I calculate that?
Is that the A of t equals A0 e to the negative AT?
That is correct. So we would take e to the minus kt. Oops, jeez, t. All right. So my initial concentration is 0.0240 molar. And e to the minus k is equal to 4.82 times 10 to the minus 3 inverse seconds. And multiply by 481 seconds. And that'll allow me to calculate what the concentration will be at that later time. Ooh, anybody have an answer?
3.01 times 10 to the negative 3.
I think it's 431 seconds.
Oh, 431. Okay, so screwed that one up. And what did you get for that answer?
I got 3.01 times 10 to the negative 3.
3.01 times 10 to the minus 3. All right. Anybody have any questions about that?
Is the units just molar?
Yes, molar. Because the units on the initial concentration are molar. All right. The thermal decomposition of phosphine into phosphorus and molecular hydrogen is a first order reaction. The rate constant is 1.98 times 10 to the minus second. How long will it take for the concentration to decrease from 3 molar to 1 molar? You know how to do that? All right, then let's forget about that. Nah, we can do that one. Now, how would you do that one? Well, I see there's another one just like it. So I'll let you do that one on your own. How would I get it? I want to solve for T.
Just do that same equation above and just rearrange it algebraically for T.
So the minus 1 over K log of pH3 at time T divided by pH3, 0? That look right? So that's minus 1 over 1.98 times 10 to the minus 2 inverse seconds times the log of, okay, so we started with (3 molar) and ended up with 0.1 molar. All right, so that will tell us how long we need to wait until the concentration will drop. Maybe that's when it's safe to go in, right? 3 molar, got to go in when it's 0.1 molar, after it's dropped below 0.1 molar. Oh, shoot. Don't want that. Anybody got a number?
171.77.
Okay, how many digits are we good to? 3. So 172. All right. Look at problem number 8. A reaction that is second order in NOCl is 90% complete after 450 seconds. If the initial concentration 1.35 molar, what is the rate constant, including units?
So you're looking for K?
Pardon me?
So you're looking for K?
Yes, rate constant K. Anybody know where you'd start? Yes.
Rearrange the equation as well for K.
Which equation?
The second order equation.
Okay, so we've got 1 over a at time t is equal to kt minus plus 1 over a naught. All right, so solving for k, it would be 1 over t times 1 over a at time t minus 1 over a naught. That look right? Algebraically? Take this, divided by, take this, subtract off that, and then that would be divided by t. So my time is 450 seconds. And what is a naught?
1.
Well, let's see. Yeah, a naught is 1.35 actually. 1.35. And what is a at time t? It says it's 90% complete. It's gone 90% of the way.
90% of 1.1.
Yeah, so 90% of 1.35, which means 10% is left. So that's 0.135. And so, is that 0.0148? And what are the units on that?
Seconds to -1, or inverse seconds.
Inverse seconds to the -1. Molarity.
Oh, molarity per second.
Moles per liter per second?
Is it molarity to the -1?
Yes, it's molarity to the -1. It's second order. N is equal to 2. Remember units on a rate constant. Molarity to the 1 minus n, seconds to the -1. So it's a second order process. So 1 minus 2 gives me -1.
Would K be negative?
No, this is a bigger number than that. One over that gives you a bigger number. And K's are negative, never negative, just to give you a tip. If you come out with a value of K that's negative, you've done something wrong. All right, question number 10. This is directly from an old quiz that I gave. NO2 reacts as shown. What is the order of the reaction with respect to NO2 in the rate law? What is the order of the reaction? Second order. And how did you get that? Because one over the concentration of the reactant versus time is a nice straight line. All right, if this one had been a straight line, it would have been first order. If this one had been a straight line, it would have been zeroth order. What is the rate constant, including the units? Yes, Schneider.
0.6324 molarity to the -1 seconds to the -1.
That is correct. Very good. The slope is equal to the rate constant K from that plot. All right. Reaction mechanism. All right. Reaction mechanism are the steps that occur in a chemical reaction which results, the elementary processes that occur that results in the overall chemical reaction. Right? So it's a step-by-step way that the reaction occurs. Right? So a series of elementary processes an elementary process is an actual collision which results in the overall chemical reaction. Okay, that's called a reaction mechanism. Right? So, when you look at a balanced chemical reaction, that does not tell you how the reaction actually occurs. Right? A mechanism is telling you what actually the process that occurs. So, an example of a two-step mechanism. NO2 plus NO2 goes to form NO3 plus NO. That's the first elementary process. Then the NO3 reacts with CO to form CO2 plus NO2. This is a two-step mechanism. And an elementary process actually represents a collision. So this mechanism is saying, all right, I got an NO2 molecule and an NO2 molecule. They come together and they hit. And in that collision, one of those oxygens gets transferred to one of the NO2s, and the other NO2 loses its oxygen. And so they fall apart, leaving you with NO3 and an NO molecule. Okay? Then, that NO3 molecule that was produced in the first step collides with a CO molecule. So here's a CO now coming along and hits that NO3. And when they collide, the NO3 transfers one of those oxygens over to the CO2, the CO, to make CO2 plus NO2. All right, so one of the things when you're given a mechanism like this, you need to be able to figure out what the overall chemical reaction is. All right, so what is the total chemical reaction that's occurring that we would write if we're doing a stoichiometry problem? We'd be given just what the reaction is. What is the reaction that results from this two-step mechanism? All right, so what you would do to determine this is you'd cancel out things that show up on both sides. All right, so an NO2 cancels with that. And so we're left with NO2 plus CO goes to form CO2 plus NO. So there's the balanced chemical reaction. All right, this thing right there is called an intermediate. All right, an intermediate is species which is present in the mechanism but not in the balanced equation. Species present in the mechanism. All right, maybe I should say formed. Species formed in the mechanism but does not occur or is not present in the overall equation or reaction. All right, so it's formed in the mechanism, but then it's also removed in the mechanism, right? And so that's called an intermediate. Doesn't appear in the balanced chemical reaction, but does appear in the mechanism. All right, that's called an intermediate. Let's actually want to look at what I'm supposed to cover here. Make sure I get everything. When you have a collision, there are certain names for these things. Let's see if we got to cover that. All right, so given a reaction mechanism, identify reaction intermediates and catalysts, write the overall reaction, determine the molecularity of each step. All right, so molecularity. If you have a reaction that goes like this, if that's a step in the reaction, that's called unimolecular. All right, because only one thing shows up on the left-hand side. If you have A plus B goes to form products, doesn't matter what it is, that's called bimolecular. Because two things. If you have A plus B plus C, or 2A plus B goes to form products, there are three ways you could do this, actually. Products, or 3A goes to form products. Actually, there are actually two ways this could happen. This could be A plus A goes to form products. Both of these would be bimolecular processes. If an A collides with another A in the mechanism. That's bimolecular. What do you think this one's called? That sounds like a very reasonable answer. Turns out that's not correct, but very reasonable. It's called termolecular.
Jesus.
Okay? That's called termolecular. When two things collide bimolecular, one thing kind of falls apart, then it's unimolecular. Right? And so in both of these steps, you have what kind of process? Bimolecular. That's a bimolecular process, and that's a bimolecular process. That's very common. Most likely in a reaction mechanism, it will be a bimolecular process. Yes?
So the only part that matters for this is the reactants.
Is the reactant.
I mean, no, it's like the left side.
On the left-hand side, yes,
Yeah.
that's correct. Yes. In order to describe a step in the mechanism, the only thing that matters is is what's on the left-hand side. That's correct. All right.
So could you move the page up?
Sorry. So that is as much as we need to talk about in terms of mechanisms. Going kind of light on that, because the only thing we're really going to worry about is something called a catalyst. So if we look at energy requirements, something called reaction coordinate diagram or stage of reaction. Stage of reaction diagram. All right, so here we've got energy, and over here is a stage of reaction. Okay? So, for an exothermic process, let's say I've got the reactants here. Let's say this is an A plus B goes to form C plus D. Here's the energy of the reactants, A plus B. For an exothermic process, where will the products be? Higher? Over there? Lower. Right, so over here we've got C plus D. But what happens in between? Well, normally for most chemical reactions, in order for the reaction to start, some of these bonds in the A and B molecules have to be kind of stretched out in order for the reaction to proceed. What is required to stretch a bond? Energy, right? So what happens is there is a barrier that's required to either stretch or break a bond initially, and then once that process occurs, it reaches what's called the activated complex. That's when it will fall into products. Okay? So there's some minimum amount of energy, this amount right here. We call that the activation energy. All right, so activation energy, given the symbol E sub A. All right, it's the energy required for the reactants to proceed to products. Right? If you have A and B and they're coming along and they collide with less energy than that, right, they'll kind of go up but then fall right back down. They'll bounce off each other and nothing happens. If there's enough energy in their collision to get up above the activation energy, then they fall over into products. Right? So that's called the activation energy. If instead you have so this is an exothermic process, what is the value of delta H or delta E in that diagram right there? Okay, it's going to be a negative number, and we would show that as
C plus D minus.
it would be E sub A plus that distance all the way down there. That's that distance right there. Let's just call that delta H, which in many cases equal to delta E. Exothermic really refers to it. Right? That would be a negative number. Delta H is equal to negative. And it would be that amount right there would be the exothermicity. All right, if it's endothermic, all right, so here's my reactants, A plus B. Where are my products going to be? Higher now. And so you'll have that going to form C plus D. And this value right there, what do we call this thing right there? E sub A, that's the activation energy. And that amount right there is delta H. In this case, it's a positive number. All right. So that's a representation of what happens as a reaction proceeds to reactants and products as we go through this reaction mechanism that's occurring. Okay. Now, what does a catalyst do? Okay, so it speeds up a chemical reaction. All right, so catalyst speeds up the reaction rate by doing what? Yes?
It lowers the activation energy.
That's correct. By lowering the activation energy. All right, that is a catalyst. So if we look at this chemical reaction right here, and I now add a catalyst, let's say the activation energy is now that right there. Sorry. All right, so now the red doesn't show up very well, but that's actually red now. And so this represents the lower activation. That's the activation energy of the catalyzed reaction, right? So there's the uncatalyzed, there's the catalyzed activation energy, right? And then the same thing would happen here. Catalyzed reaction is lower because it lowers the activation energy. So that right there is E sub A catalyzed. Now, why does that speed up the reaction? All right. Anybody remember from last semester something called the Maxwell-Boltzmann distribution?
No.
No chance. Huh? Nope. All right. All right. So this is called the Maxwell-Boltzmann distribution. And it represents what the molecules, the speeds of molecules as a function of temperature. So it will look something like this. If this is T1 and T1 is less than T2, what will T2 look like? Right, as I raise the temperature, what happens to this distribution? Yeah, it goes like this. The speeds go higher. Okay. All right. This speed, let's say that for a particular chemical reaction, let's focus on, so this is T2. Let's focus on just this T1. Let's say this represents the activation energy uncatalyzed. Okay? Then, now, I guess I didn't describe what what does this mean, right? If I take let's say that's 100 meters per second, 200, 300, 400, 500, all right? If I take the area under the curve here, what does that represent compared to the entire area? Anybody know what the area under the entire curve is? It's equal to 1. All right. Let's say that the area between 100 and 200 meters per second is 0.2. What does that mean about the molecules that distribution has? Yes, Schneider?
5% of the molecules in reaction. I found that like
Well, 20% of the molecules in that sample will have speeds between 100 and 200 meters per second. Right? If that is 0.05, that means that 5% of the molecules have speeds less than 100 meters per second. If going over from here to there is 40%, then 0.4, then 40% of the molecules are between 200 and 400 meters per second. Right? So that's what a Maxwell-Boltzmann distribution tells you, is what percentage of the molecules falls between two different speeds. Okay? Well, somewhere along here, a speed will correspond to an energy, 1/2 mv squared. Let's say that that speed that's required to get over that hump corresponds to right there. Okay, then what fraction of the molecules then have the necessary energy to go above get past the activation energy? The ones over here. Okay? That's how many will make it over the barrier to react. All right, now I add a catalyst. What does the catalyst do? It speeds it up by lowering the activation. So now let's say right here is the activation energy for the catalyzed reaction. Okay, so why does it speed up the reaction? Because now this many molecules, right? There's an additional number of molecules that have the necessary energy to get over the barrier, right? So that's how that speeds that up. What does changing the temperature do for a chemical reaction? This is something we'll cover next time. What does changing the temperature do to the chemical reaction? It increases, because now if you compare the uncatalyzed reaction, this many molecules have the necessary energy to get over the barrier. At the higher temperature, how many do? All that extra space there, that many molecules. So by raising the temperature, it increases the number, speeds up the chemical reaction by increasing the number of molecules that have the necessary energy to go above the barrier. Okay, so still have 8 minutes left. So I left a couple of those problems blank. If you want to try and get a point added to your quiz for Thursday, then go ahead and attempt to do those 2 problems that we didn't cover, which was problem, 4? No, not problem 4. Number 7 and 7 and 9. Do problem 7 and 9. Bring it up to me. If you got the right answer, I'll give you a point added to your quiz on Thursday.